record is starting from in here. Okay. And then these three material is a combination of this material. They are used for the device. Okay. As you learn in the 339 is as a semiconductor for our material, we typically interest in the silicon. Okay. And then the semiconductor has the characteristic of structure, which has its valence band and the conduction band. They are separated with the so-called energy gap. And then this energy gap is reasonably small, so that the electron in the valence gap, when they get the energy, they can jump to the conduction band, so that we can see the current flow through the material. So that is we call the semiconductor. Similarly, we have also is called the insulator. Okay, insulator case has also similar this valence band and conduction band. Okay, but their energy gap is much larger than the semiconductor. So often this energy gap is very high, so the electron is very hard to jump to the conduction band. Mitchell, do you have any question? I see.
Yes, Professor. I have a question.
Yes.
So I've been reading a lot more about quantum mechanics and physics.
Yes.
And I want to ask, everyone's familiar with the atom and how it has, there's a nucleus and there is orbitals around. And
yes.
The electron can only travel within the orbitals and not in between. Okay. Is that the same concept here with the valence band and the conduction band?
No.
As in so the electrons can exist within the energy gap, or it can only be between the valence band and the conduction band?
So in the electron gap is that the electron cannot exist in between this energy gap, because simply is that in the energy gap is we call the density of state is not exist in here. Okay, so the electron cannot be exist in the energy gap. Okay, so that is the one answer for your question. And then another one is, for example, is when you look at the silicon, okay, silicon as the single atom, it has the different this orbit, as you point out, right? And then
Yep.
when you look at this orbit in here, is that is, as you know, electron is occupying with a certain rule for this each orbit, right? Okay, and then in our case, when we discuss about the conduction band, valence band, we are looking at the most outer orbit of this silicon atom. Okay, so silicon case is that this is what we call the column. Is column 4 is a material. So which means that the most outer of it, this one has the 4 electrons exist. Okay. And then when this silicon is interact with the other silicon atom, and then this outer orbit, this electron interact with the other outer orbit electrons. Okay. So when we discuss about this valence band and the conduction band, we are talking about this most outer orbit of this atom. Does that answer your question?
Yes, it does. I just find the concept really interesting because when you say that the electrons jump, one question I have is how fast does it travel when it jumps? And maybe you have an answer. Does it travel faster than light when it jumps?
That one is probably we're gonna discuss more when we discuss the device. But it depends on the is a different physics. It depends on the how fast this energy is going into the semiconductor, and then that allowed to this jumping of this electron from valence band to the conduction band.
Okay, and Professor, I have a question. So when the electrons jump, do they follow classical physics or do they follow quantum physics?
It still is combination.
A combination.
So,
Nice.
which means that on top of conduction band is that we can treat this one as the like a particle movement when we have the certain electric field applied through the structure. But at the same time is that the movement of this one following this wave behave of this movement. So which means that is later on is we're going to also discuss we can create some kind of energy wall through the device, and then in the classical physics, electron can go to the other side is only way to this go over this energy wall. But in the some application, is actually electron is passing through this wall. And then this kind of passing through is following this quantum physics is some applications. So we're going to treat this movement is both way.
Cool. Thank you so much, Professor. I just find this concept really, really interesting. That's why I asked.
Yes, that's good. Yeah, that's good. I think during the class is ask, whatever you have in mind, you can ask. If I can answer those questions right away, then I try to answer. If not, maybe I can follow in the next class. Okay. So that way.
Perfect. Thank you.
Okay, that's good. So in the class is especially for this device, we're going to use this three material to form the device. Okay, so okay, and then this is the I think you guys already covered in the 339, especially for the electronic this device. We're going to more focus on the silicon material. Okay, so silicon, this is a choice for our semiconductor material for the device. And then when you look at the silicon, especially as you know, is that for the device, we're looking at the silicon as the crystal structure. So which means that this silicon atom in here in figure is actually showing that the structure of this silicon crystal, they have the certain arrangement of this silicon atom to form the crystal. And then often this one follow that is similar to the diamond, this structure. So that the silicon, this crystal structure, sometimes we call the diamond structure. And then when you look at the diamond structure, and especially in the cubic, this kind of structure, we can see that how this silicon atom is arranged. So if you look at this arrangement, is that in the cubic structure, each corner, we have this silicon atom exists. And then there's another area, especially in the face of this cubic, we will have also is that the atom going to be exist. And then this face centered cubic structure is somehow is overlap to form this silicon crystal structure. And then that is specifically we call the diamond structure and form this silicon structure. And then when you look at this silicon crystal structure, especially this nearest these two atoms, we actually define that the so-called lattice distance between the atom. And then in the silicon case, that distance is this number. Okay. So based on this lattice distance is open when you have the cubic centimeter of the silicon crystal structure, we can actually estimate how many this silicon atom will be exist within this cubic centimeter. Okay, so that kind of calculation we can have. If we have the different semiconductor also has the different this lattice distance. And then, for example, germanium is also different type of semiconductor material, and that has this number of lattice distance. Okay. So now, if you look at the silicon crystal structure as more in detail, is if we look at silicon, as you can see, as a silicon crystal structure, we have a silicon, and then near this silicon is you have another silicon. Okay, so as I mentioned, is a silicon is a column 4 material, which means that the number of electrons in the most outer orbit is going to be 4. So 4 electrons going to be exist in the most outer orbit for this silicon atom. And then each this electron, they are shared with a neighboring electron from the neighbor silicon atom. Okay, so by that way is that in this orbit, they can have the 8 electron exist, so that they stay as the stable this bonding structure. Okay, so especially in the semiconductor this material, we have technology, especially fabrication technology, to introduce the so-called impurity, or we call the doping. So using the doping process, sometimes we can introduce the column 3 material. So which means that the column 3 material means that the number of electrons in the most outer orbit for that material going to be 3. So one example is in here showing as the boron. Okay. So boron is a column 3 material, and then it has only 3 electrons. So when the boron introduced the silicon crystal, so that this boron replaced one of the silicon atom, then what happened is 3 electrons from the boron, they are shared with the neighboring silicon atom, but it has the one missing this electron. Okay? And then especially this one is we can say this is the hole. Okay, and then later on I'm going to describe that this hole is also used for transferring of the other electron through this crystal structure. Okay. In the other case, we can also introduce the so-called column 5, the impurity or dopant. So column 5 means that the outer orbit, the number of electrons going to be 5. So which means that in here, as an example, if you look at the phosphorus atom, it has the 5 electrons in the most outer orbit. So 4 of them shared by the neighboring silicon atom, and then you have additional this electron in here. And now is this additional electron, because this is not shared by the other silicon atom, when you apply the electric field in this structure, this electron, because this is the charged as a negative, so that they can be moving around in the crystal structure. Okay? And then that later on we're going to discuss is contribute the current flow through the material. Okay? So that briefly described this silicon crystal structure. When you look at the pure silicon, so pure silicon means that, let's say we have silicon, there's no impurity within this pure silicon. In this case, as I mentioned, each silicon atom, they have 4 electrons in their most outer orbit, right? So with the neighboring silicon, they can share each this electron. Okay, so by that way is that all these electron in the outer orbit, they are shared, and then they create a very strong bonding within this crystal structure. And then this kind of bonding we call the covalent bonding in this structure. So for this case, because each electron, they're shared with the neighboring silicon atom and then strongly bonded in the crystal structure, when you apply for example, is the potential through the material, this electron does not move throughout the structure. So often we see that in this material, when you look at the resistance throughout the material, that resistance is going to be very, very high, okay? Because there is no these extra electrons contribute the current flow. Okay? So that's the case for the pure this silicon atom. Now, as I mentioned, is that if we introduce the impurity into this silicon atom, now, for example, is a phosphorus. This is column 5 dopant, which means that the most outer of it has actually 5 electrons available. Okay? So 4 of them is shared by the neighboring silicon atom, and then you have this excess electron. Okay. Now, this excess electron is that actually still bounded by this phosphorus, this dopant, but this is not shared by the other silicon atom, so that when we apply for example, voltage throughout the material, this one can moving around throughout this crystal structure. And then that creates the current flow in the material. So that's the case is that we call the N-type silicon. And then meaning is that the N-type silicon, you have lots of excess electron exist. Okay. And then open is that when you look at in the device, when this each phosphorus atom ionized to create each excess electron, then from this doping concentration, we can estimate the number of this excess electron. Okay, so that's we're going to discuss later on. So for the N-type silicon case, as I mentioned, we have lots of this excess electron exist throughout the structure. So, for example, in the material, if you apply the this bias potential, such a way that you have a positive and negative you apply, then electron itself is negatively charged, so that they moving to this positive side of the power supply. Okay, and then when the electron move in this direction, we can say that the current flow is going into the opposite direction. Okay, so that way is that we can see is current flow in this N-type silicon. Now is instead of this column 5, if we use the column 3 material, which means that in the outer orbit it has the this 3 electron exist in the outer orbit. Okay. Actually, this is not. This is from in here. Then you can see is that 3 this electron shared by the neighboring this silicon, and then you have one missing this electron in here. Okay, and then that is we call the hole. Okay, and then this hole is also we can treat as the movement within this silicon crystal structure. So such a way that now we have the empty space in here. So which means that one of this neighboring electron can jump to the this empty space, so that that effectively translate the hole is moving to the opposite direction. Okay. So for this type of semiconductor is we call the silicon p-type silicon in here, which has the lots of holes exist in the crystal structure. So for the hole is this figure is basically illustrate how the hole moves throughout this silicon structure. So this is the basically is, for example, is let's say if the electron in here that goes to this empty hole side, then now is that area is filled with electron, and then previous that site which occupied the electron, that is now empty like this. Okay, create a hole, and then another electron moves in here, then now is hole moved in here. Okay, so effectively is that even though this one is that electron is moving to occupy this hole, but we can effectively think is that this empty space is actually moving in the opposite direction. Okay, and then that way is that we can describe as the hole movement in this silicon crystal structure. Okay. Okay, Michael. Yes, you have a question?
Yeah, I have a question, Professor. So over here we see on the bottom, the right corner, we see the path that this hole, although the hole is not moving, it's actually the electrons are moving to the left rather than the hole moving to the right.
Right.
Is it always the path that the electrons will move, or is this just like a interpretation of how it might move? Do we know exactly how it moves?
This is just the example. Is that okay. There are lots of different ways. Is that but for example, in the general is let's say if we have this kind of a crystal structure, and then if we apply the potential in the material, so generally for this case is that in the electron is, as you know, is a negative charge. So negative charge is that try to move to this positive direction, so that is that any electron can going into this hole and then moving that direction. So this illustration is the one possible the path, but there are many different paths can be exist.
Thank you very much.
Okay, that's good. Okay, so is that in the p-type silicon, is that when you look at this path, is that as you can see, is that we can visualize is that the electron moves in this through this hole. So electron flow in this direction, and the hole flow in the opposite direction. Okay, and then typically is that when we describe that the current in the device, the current movement direction follow the same direction as the whole movement direction. Okay, in other words, is that the opposite direction of the electron movement. Okay, so that is what we describe for the current flow direction. Okay, so this is the kind of summary as the different type of dopant we can use for the silicon. Okay, so silicon, as I mentioned, is if you look at the periodic table and then look at silicon, silicon is within the so-called group 4.
In California.
Yes. Okay. Hello? Do you have a question? Okay. Silicon is, we call the group 4 material, which means that, as I mentioned, is that most out of it, you have 4 electrons exist in this material. Okay. Now, in the previous description, as you know, as a dopant, we can use the group 5 or group 3 material. When you use the group 5, which has the 5 electron exist in the most out of it, going into this silicon crystal, then you have 1 extra electron exist in here. Okay, so when you form the silicon structure with this group 5 dopant, that create lots of excess this electron available, and then that we call the n-type semiconductor. Now, if we use the group 3 case is that we have only 3 electrons available and the most out of it. So when you put this group 3 dopant into the silicon structure, you have the excess hole is available in this material structure. And then that is we call the p-type semiconductor. Okay. Now, if you look at the periodic table, is in the group 3, we have the different choice of this atom available. For example, boron, aluminum, gallium, indium, they are all group 3, this atom. So which means that they all have the 3 electron available on the most outer orbit. So technically, you can use all of these the column 3 material as a dopant for the silicon crystal. Okay, but typically we have choice is that we can use the certain this atom is more preferred as a dopant. That preference is that it depends on how well we can control of this doping in this crystal structure. Okay, so that one is I will describe a little bit later on. Okay. So same way is that if you look at the column 5, we have the nitrogen, phosphorus, arsenic, antimony. They all belong to this column 5, this atom. So which means that in the most outer of it, you have 5 electrons available. So again, theoretically, you can use any of these column 5, this atom, as the dopant for this silicon. Okay, but typically we have also is a prepared dopant exist for this silicon. Okay. Now that question is, as I mentioned, is how well we can control to this silicon. So for example, is that the very simple way is we perform the doping is, let's say if you have a silicon, so you have a silicon piece, okay, and then if you want to have the doping is on the surface of silicon, some area is we put the so-called masking layer. Typically, masking layer is we can use silicon dioxide or sometimes silicon nitride. Okay, there's the kind of insulation layer, and then we put this material into the furnace. It's a very high temperature furnace. So let's say it's the 1000 Celsius of the degree in the furnace. Okay, and then in this hot furnace, we introduced the dopant. So for example, is that let's say we introduced this phosphorus in here. Okay. So when we introduced in phosphorus, now this phosphorus, this atom, is now diffused through this silicon. Okay. The masking area, this one is effectively blocked this diffusion of this phosphorus. So when we control the temperature, and then when you control the time in here, now we can actually see is that how deep this phosphorus diffuse through this silicon material. Okay. Now, some of the atom is that we can control this diffusion is very well. But some atom depends on the size of the atom. Is, as you know, if you go to in here, the atomic number is getting bigger. So which means that the size also is bigger. So those atoms is sometimes very hard to diffuse through this silicon material. So you cannot actually create this doped area effectively into the silicon crystal structure. So this kind of, okay, readily, do you have a question? No? I saw you raise your hand. Okay.
Oh, wait,
So
wait, wait.
depend.
I thought I was talking. I was muted. My bad. I'm sorry.
Oh, okay.
Yes.
Oh, that's.
Like,
Do you have a question?
yes.
Okay.
So when you diffuse the other element into like silicon, does
Mhm.
it diffuse in different atoms match with the one atom of silicon, or does it like it's random? So it will be phosphorus still with another atom phosphorus then it's a silicon, or will it be silicon, phosphorus, like this?
Oh, it's random. It's actually is you know that the silicon crystal structure, as I show, right?
Yes.
So is when the silicon is formed the crystal structure, they have a certain exact location of this silicon atom. So as I mentioned, that is I mentioned in the beginning, it has the diamond structure. So exact location, I mean the specific location, silicon is exist. Okay. Now, when you introduce the, for example, phosphorus in here, one of the silicon, this atom, replaced by this phosphorus. So when they replaced, that is the basic random.
What happened to that silicon atom then?
So this one is actually is detached from the crystal structure.
Oh, okay.
So it's just is randomly
So you
is
saw
replaced.
atom floating in outside of crystal structure now, the silicon.
It's not like that. It's more like initially for example when the phosphorus going into this structure,
Mm-hmm.
they randomly exist in the crystal structure, but when they reach to the so-called equilibrium,
Yes.
and then the crystal is try to individual the atom, they try to balance the energy and then going into the minimum energy state. So that they actually happens that this phosphorus impurity atom replace the silicon, and then that is happen.
But what happened to the silicon?
So that is the going somewhere in the outside in the crystal.
Oh, okay. It's okay.
Yeah. So
Right.
that's the kind of thing happen. Especially so it's as I mentioned is a very high temperature. So is that that released actually this solid structure in the material.
Okay. Thank you.
And then when you cool down, is they going into this solid crystal structure. Okay.
Okay. Thank you. I understand.
Okay, that's a good question. So that way is that is we can replace, but as I mentioned, is that this kind of replacement of the silicon atom with impurity depends on the characteristic of this different atom. So which means that some of atom is that we can actually control is very well for this diffusion process. So with the correct control of the temperature and the time, we can expect that how deep this impurity is going into the silicon, and then replace some of these silicon atoms. Okay, it's Mitchell, you have a question?
Yes, Professor, I have a question. So if we put the silicon inside of this furnace and then we also add phosphorus, does it depend on, for example, if we heat up this furnace to 1,000 degrees Celsius, does that depend, if we increase the temperature, the phosphorus will go deeper, or does the phosphorus go deeper through the silicon the longer it stays at 1,000 degrees Celsius?
Yes. So is roughly is that people for the silicon, they have the just 1 second. They have some kind of chart. Sorry. Yes. Okay. Just 1 second. Oh, I cannot. So there is a chart is showing that, for example, let's say this is the depth for the silicon, and this is the initial concentration of the dopant. So depends on the temperature and the time, you can actually have some kind of this different distribution. So generally, if the temperature is high and then time is longer, then as you expected is that your dopant can go into the this silicon material much deeper than the is a lower temperature and shorter time. So that way is that you can control.
Thank you very much.
Okay, yeah. So, but as I mentioned, key point for in here is, okay,
Hi, I just had a quick question. Yeah.
Okay.
Yeah, Janelle, I had a quick question. So deeper will mean more even distribution?
No, it's not necessarily even distribution. Is that, for example, is that in the device later on, let's say if you have the one example, N-type silicon starting in here, and then I want to create the P-type silicon in here, okay? So to create the PN junction diode is that I want to make the P-type silicon in this area in here. Then we introduce the dopant in here. So when you introduce the dopant, obviously, as you can see, in the reality, your concentration of the dopant close to this surface will be much higher than this lower area. So it does not actually show that the uniform distribution of the dopant, the doping. Okay. Okay, then that's good. So the reason is I'm pointing out this one is especially is now is when you look at the device size is getting smaller and smaller. Part of the reason is that the smaller device can give us the faster operation of the device performance. So to me, that means that the device, this dimension is getting smaller and smaller. So for those smaller device, now control of this diffusion need to be very precise. Okay, so that create now our is a prepared choice of this dopant in the material. So boron, phosphorus, arsenic, those are typical choice for the dopant for the silicon. And then some of the dopant is also in the red in here. They create the so-called chemical reaction with the silicon. So that does not actually used as a dopant in here. So from this kind of requirement is that we have this prepared this dopant for the silicon. Okay. Now silicon is that very well established as a electronic device, and then often is when you choose the different dopant is that we can have the so-called this kind of curve. Just 1 second. Just 1 second. Oh, somehow. Okay. Somehow they all highlighted in here. Okay, let's just do. Okay. So for the silicon, okay, Michael, you have
I have a question. Is silicon in the raw form, is
Yes.
it conductive, or is it only becomes conductive when we dope it with impurities?
Oh, it's the resistance. If you just have the piece of the silicon,
Right.
and then if the silicon, this is a pure, so and as you measure the resistance of this silicon, that resistance is going to be very, very high.
Okay. But
So
if you
it's
connect
more
like
like an insulator.
if you connect the battery from the left and the right side,
You
like
do
a
not
circuit,
see the current flow through this material.
you will not, right?
You will not.
Okay, cool. Thank you.
So now is as you doped in this silicon, now depends on the level of doping, you can actually expect that this kind of resistance depends on the doping. So for example, let's say P-type dopant that is often followed this line. So when you have the higher doping, let's say 10 to 19 atoms per cubic centimeter, you can expect that that resistance is going to be somewhere in here. 10 to negative 2 ohm centimeter. Okay.
Awesome.
If you have lower doping, as you can see, is a very small amount of atom, 10 to 14 atoms per cubic centimeter, the resistance is going to be this one. It's very high. Okay. So something like this. So silicon case is that actually this kind of graph is very well established. So you can roughly estimate from the measured of your resistance of your sample, you can actually estimate the doping concentration of the material. Okay, yes.
I have a follow-up
Rachel?
question. Are
Yes.
resistors semiconductors?
You can create the resistor using the semiconductor. So
Okay,
which
so it's
means
possible to do that. But is it like regular resistors that we have in electronics? Are those specifically semiconductors, or is that just one form of a resistor you can make?
is you can create a different resistor, but the open is that when you look at the electronic circuit, the electronic circuit is built and all in the silicon is a substrate. So on top of silicon substrate, you create the transistor, PN diode, and then resistor and capacitor and everything. Okay, so to create the resistor, you can actually use a silicon material with the insulator and then the different type of metal too.
That's awesome. Thank you.
Yeah. So even as you know, if you have the metal itself has the kind of some kind of resistance. So if you control the dimension of the metal, you can actually form the resistor too. Okay. Okay, then that's good. So this is the one way is that you can estimate from the resistivity of the silicon. You can estimate the doping. Okay. So sometimes in the practical case, when you have the small piece of silicon, so in the small piece of silicon is you can actually measure the resistance, surface resistance of the silicon. And then from there is that you can estimate the doping of this silicon. Okay, that's good. Now, as I mentioned, is that we have N-type and P-type silicon. Just 1 second. Let me. So why is this is somehow is highlighted in here? Just 1 second. Okay, it's gone. Okay. So as I mentioned, we have N-type, P-type silicon. N-type silicon is that we have lots of this free electron or excess electron exist in the N-type silicon. P-type is that we have lots of holes exist in this material. Now, if you look at the origin of this electron and hole, so for example, N-type silicon, origin of this electron is coming from the dopant. So for example, if we use the phosphorus, phosphorus has, as I mentioned, it has the extra electron, okay? So which means that this extra electron coming from your phosphorus atom. So for example, let's say if the phosphorus lose this electron, now phosphorus itself is turned into the positive charge, okay? When they have combined together, now this is a neutral. Neutral means the zero charge, okay? So the phosphorus in here is that because this is within the crystal structure, we call this is immobile as a charge. So similarly, is if we use arsenic, we have this positive, this immobile charge exists. Now, electron is in here because it can be moving around through the crystal structure. We call the mobile electron in the structure. Okay. So that's the case for the N-type. Similarly, if you look at the P-type, P-type case, you have now is you have, for example, boron. So boron is that, as you see, is 3 electron is there, and then you have 1 hole is associated with the boron. Okay. Now this hole is moving around through the structure, and then this one is we call the P-type. If the boron lose the hole, then boron itself is charged as a negative charge. Okay. And then this boron is, as I mentioned, this is within the crystal structure. So this is always stay as the immobile charge. And then this positive hole is we call the mobile charge. Okay. I guess today maybe we're gonna stop here. I'm gonna revisit this one, and then we're gonna start from this slide for the next class. Do you have any question for today's class?
Yes, Professor, I have a question. Are you going to upload these slides on Blackboard?
Yes. So you will see all the slides will be uploaded on the Blackboard, so you can download. Perfect. Okay. Then that's good. And then also is that we're gonna also record the class, so you can also watch the video too. Okay.
Perfect. Thank you.
That's good. Any other question before we go? Okay, that's good. No question. So then I think that's good for today. So we're gonna meet this Wednesday. Okay. Thank you very much, guys. Okay.
Thank you. Bye bye.
Thank you. Have a good day.
Okay. Bye.